Hey guys, welcome back. Today we're going to continue talking about Newton and his laws of motion. And as you can see here, we're looking at Newton's third law of motion. And I know that we just went over the first law, but it's a lot easier for us to understand if we skip around and say, okay, we talked about the first law of inertia, first law of motion, which was the inertia law, and let's go ahead and do the third law. It's easier for us to understand. It's a more logical thought process. All right, so Newton's first law, as you recall, was the law of inertia. It says that an object in motion is going to stay in motion, or an object at rest is going to stay at rest, unless an outside force acts on it. So with the third law, we start talking about those interactions of forces, okay? So according to his third law, it says that when one body pushes on another body, the second body pushes back with an equal and opposite force. So third law says for every action, there's an equal and opposite reaction. What that means is for every force that acts on an object, that object that is acted upon has a reaction force. So in this case, we're talking about two different objects. So for every force, there's got to be an equal and opposite reaction force. They never balance each other out because they're acting on different objects. So if I have a book and the floor is holding it up, or say a table. The table is holding it up and gravity is pushing it down. They're both the table and gravity are acting on the same object, the book. But in Newton's laws, it would be the book is resting on the table and the table pushes back up. So the table exerts a force on the book and the book exerts a force on the table. And they don't cancel out because they're different objects. So if we have an example here, we have a hammer striking a stake, and the action, I guess you could say, is the hammer strikes the stake, and the reaction is the stake pushes back. It reacts by striking the hammer, and you can feel that when you're hammering in a nail. You can feel the nail resisting. Example: we got a book resting on a table, and we're going to show the forces on the table and the reaction forces. So we've got our normal force by the table on book and the gravitational force by the earth on the book. So the net force is 0. So what we're showing here is my force diagram, or my free body diagram. We have a normal force here and a gravitational force down. These are acting on different objects. So the action is the force of the table on the book, and the reaction in this case is the book on the table. So the table hits the book and the book pushes back on the table. Okay, so if A exerts a force on B, then B is going to exert a force on A. So I sit in my chair, and my chair pushes back. That's it. A force is a push or pull, we know that, and it results from interactions. So these forces result from interactions. When I sit in my chair, my body pushes downward, and then the chair pushes back. These are the two forces from the interaction. These are my action and reaction. You can't touch without being touched. That's what this says. So we think about birds. So how do birds stay in flight? They use their wings, right? So their wings push air downwards, and in turn, air pushes the bird back up. So because the force of the, let me start over. So the size of the force on the air is equal to the size of the air on the bird. So the direction of the force that the bird applies is downward, and since it applies a downward push on the air pushes upward against the bird's wings. So this is an action-reaction pair, and they make it possible for birds to fly. In summary, Newton's third law of motion says that for every action force there is an equal and opposite reaction force. Equal just means their magnitude is equal, and opposite means they're in a different direction. So I push down on the table, and the table pushes back up on my hand. So here we've got the ball hits the bat, and the bat hits the ball. And here we've got two guys, A and C, kicking a football. So A kicks the football. B, the football, pushes back on A's foot. Also, C pushes on the football, and the football pushes back on C's foot. So A and C don't react at each other. They act on the ball, and the ball reacts with them. Okay. So we have a couple more examples here. So when you're driving down the road, because of the friction of your tires on the road, you are able to go forward. So your tires push on the road, and the road pushes you. Another example is that we have trouble visualizing is the rocket. So because we have this expanding gas inside our rocket, it pushes on the rocket, and the rocket pushes on the gas. So because of this, we're able to create lift. Okay, now we're going to go to second law. So third law was action-reaction, and now second law is the net force law, for lack of a better word. So in order for me to accelerate an object, to make an object change its state of motion, I've got to apply a force to it. So that's one thing we've been talking about. It's a common theme. So in equilibrium, we've said that there's no net force. But now there is a sum of my forces. So for net force, it's going to be, and we'll get there in a second. So Newton's second law says that the mass of an object times the acceleration of that object would equal the force that I put into it. That's a really hard way to see it. In equation form, we say that here that net force equals mass times acceleration. So the sigma we know here is the sum of, so the sum of all my forces equals my mass times my acceleration. But it's really hard to visualize that way. So what I like to do is I like to write it like this. It says that acceleration equals the sum of my forces divided by mass. So what this really means is if I have a mass and I apply a force to it, then I'm going to cause an acceleration. And depending on the size of that force and the size of my mass, the acceleration is going to change. So this says that if I apply a large force to a small mass, then my acceleration will be huge. So if I have, let's say, a force of 100 newtons and a mass of 1 kilogram, then my acceleration is going to be a very large, 100 meters per second squared, which is a huge acceleration. But conversely, if I have a very small force, if I have a 1 Newton force and a 100 kilogram object, so a very small force and a very large object, then I'm going to have an acceleration of 1 divided by 100 meters per second squared. It's very small number. And that just makes sense, right? The bigger the object is, the greater the force we need to get it to accelerate, to change its motion. Second law also, our unit for force is the Newton. And the Newton is not one of our basic units. Our basic units we have right now are meters, kilograms, and seconds. So with newtons, a Newton is a derived unit. A Newton's a derived unit. And Newton is the force which, applied to a 1 kilogram mass, accelerates that mass at 1 meter per second squared. So a Newton is 1 kilogram meter per second squared. 1 kilogram meter per second squared. So we've got our 1 kilogram object here. We apply a force of 1 Newton, and it accelerates at 1 meter per second squared. All right, so what we have, if forces are imbalanced, there will be an acceleration. If forces are balanced, so if the sum of my forces is 0, we're either sitting still or we're moving at constant speed. But now we're unbalancing our forces. So now I have a sum of my forces that's not equal to 0. So there will be an acceleration, and the acceleration depends directly on our net force, or it varies inversely with our object's mass. So if I have a big net force and a small mass, then I'll have a big acceleration. But if I have that same force and I increase the mass, then I'm going to have a progressively smaller acceleration. This tells me that twice as much force produces twice as much acceleration. That makes sense, as long as my mass is constant. Twice the force on twice the mass would give me the same acceleration. So the same force accelerates 2 bricks half as much. So if I have one small force and double the weight, I have that same force and double the mass, so it would be 1/2 of what it was originally. I have 3 bricks, so I still have the same force, and that mass is 3 times what it was. Then my acceleration would be 1/3 of what it was. So 1 over 3, 1F over 3M is 1/3 the acceleration. Just kind of makes sense. All right, so now what we're going to do is we're going to get to where we're actually working problems. So here we have 4.10. We're on page, here we are. We are on page 74, page 74 of our yellow book. All right, so our mass is 10 kilograms, and we have an acceleration of 2 meters per second squared. So what we're asked to solve for is the sum of the forces, the net force. So we have our mass, our acceleration. If we remember back, the formula was, or what we're looking for is our sum of our forces. Our formula is mass times acceleration. This is a very simple problem. So let me find our mouse here. So we're looking for the sum of my forces. My mass, I know, is 10 kilograms. My acceleration is 2 meters per second squared. So the sum of my forces, my net force, is 20 newtons. So 10 kilograms meters per second squared is the same as saying, times 2 meters per second squared is the same as saying 20 newtons. I have 20 Newton net force. So very simple problem. Anytime I'm asking for the net force, this is the equation that I use. This is given to you on your EOC. All right, so 4.11 now. We have a force of 80 newtons, so now we're given a force, and we give an object of unknown mass and acceleration of 20 meters per second. What is our mass? So now we're asked to solve for a different variable in the equation. We're still going to use the same equation, which have a different variable. So we write down what we're given. We're given 80 newtons. We have an acceleration of 20 meters per second squared, and we are looking for mass. So our formula is the sum of our forces equals mass times acceleration. So algebraically, what I would do here is I would solve for m. And the easiest way for me to solve for m is to divide both sides by a. So if I divide both sides by a, then I'm left with mass is the sum of my forces divided by my acceleration. We plug our numbers in. We have 80 newtons over a 20 meter per second squared acceleration, and we end up getting 4 kilograms. Our mass in this case would be 4 kilograms. Very simple problem to figure out. 3-variable equation doesn't get much easier than that. All right, now we've got a new guy. We've got Danny the skater. His total mass is 25 kilograms, and he's rocket powered. So this is where it gets a little bit more involved as far as our problems go. So the first thing we want to do is draw our free body diagram. So automatically we know, since Danny is on Earth, or we assume he's on Earth, that we have a gravitational force, and he's resting on a surface, so we have a normal force. So we draw Danny, then we draw from him a gravitational force, his weight, and we also have a normal force going upward. And since he's at rest on the ground, the length of my arrows is going to be the same. And we know that now he's got a force being applied in the rightward direction. So we have to put in that formula. And it doesn't say anything about friction here, so we're just going to assume we're frictionless. So here's our applied force. And the purple arrow here is our direction of motion. This is our direction of motion. So now we can see that the sum of forces in the x, or excuse me, in the y here is 0, but we don't have a 0 net force in the x. So what we're going to do now is we're going to figure out the acceleration, or the acceleration if we have a 100 Newton force. First thing we do is we complete our values. So our mass is 25. Our force is equal to mass times acceleration. The sum of my forces, the only force that I have is my applied force, so the force of thrust to the right. So what's my mass? 25. What's my acceleration? We have a force of 100 newtons, so our acceleration is our force applied divided by our mass, so 100 divided by 25 would give me 4 meters per second squared. If we do the same thing with 200 newtons, so now I plug in a 200 here over my mass of 25, my mass doesn't change, and I get 8 meters per second squared. So my force, if I double my force and change nothing else, then I double my acceleration. Makes sense. So now we're going to work it backwards. We're going to solve for force. So for our force. So we have a mass, and force applied equals our mass times our acceleration. So 25 is my mass, my acceleration is 10 meters per second, so multiply them together, I get 250 newtons. I have a force of 250 newtons, and it causes an acceleration of 10 meters per second squared.